Right, good morning. Can you hear me? Okay, great. Morning, everyone. My name's Ian de Villiers. This has basically been a little project I started off on quite a long time ago. Sort of decided I wanted to play around with smart meters and similar, sort of get myself out of my comfort zone a little bit because I generally focus very much on the application level. I'm not really a hardware hacking type specialist, but anyway, a lot of interesting stuff. I focus on a bunch of stuff. Presented back here at 44Con back in 2011. That was on SAP, but it's very nice to be back. In any case, I work for SensePost. I'm a security analyst at SensePost. SensePost, South African company. We have offices here in the UK as well. Focus very much on assessment work, training, scanning services and similar, and then also on the research. As I said, I'm a security analyst. Now, in terms of the stuff, if we have a look at why this stuff becomes very important, around the world, the countries are starting to battle with resources and similar. So you've got a bunch of things where people can feed back into the grid. I don't live in the UK or in Europe or in the US or something similar. I live in South Africa. Obviously, that means I don't have quite a perspective in terms of smart metering systems that other countries have because we've only recently started rolling them out. And that comes more as a result of, I'm not sure if people have read in the news, but we've actually been battling very much in terms of electricity generation. I've got a parastatal called Eskom, which basically has not been able to keep the lights on. In fact, I think they made it for about 40 days quite recently, but I believe yesterday they started load shedding again. Load shedding basically meaning rolling blackouts. So can't generate enough power, so we switch off various bits of the grid at various times. Now, the interesting thing about it is the way things currently work is that the system as it stands is currently also open to a little bit of abuse. And that's because we've got meters installed at home, but because there's no two-way communication between the metering system and the organization, things like prepaid electricity are a problem. This over here is actually a slip of a prepaid meter purchase. It's back in 2013. It's from my personal place, which is why I've redacted a bunch of information. So how that works is that actually there is an algorithm programmed onto the meter itself, which determines how we validate the tokens. You've got a keypad to punch in information, and then it'll go along and decrypt this and figure out is the token valid and how many units that you actually purchase. What's interesting about this is that all those underlined little bits actually are all part of the algorithm. It's a matter of public record. You can sort of go along and dig through the South African Bureau of Standards, and you'll find the document which explains how that encryption algorithm actually works. There's no validation done. It's only validated on the meter. And this means there's only one piece of information that's not on the slip, which can actually be brute forced relatively easily. So in terms of rolling out metering systems, because you've got this two-way communication, you can also start preventing fraud on people generating tokens to give themselves electricity. But what's even better about this is that you've got the same hardware being used in a bunch of stuff. So, I mean, you've got, obviously, they're used in smart meters, that's self-explanatory. But you also see them in industrial and process control, transport management, building automation, et cetera, et cetera, et cetera. And one day when I'm done, I'm going to take the meters I've got, and I'm actually going to turn them into like a very advanced garden irrigation system because I don't know what I'm going to do with them otherwise. So that's basically it. You've also got this whole thing about utility providers having a significantly increased attack surface. In the old days of metering, obviously, you've got a utility provider, you've got a consumer. There's only ever one-way communication or one-way provision through that utility. It'll obviously be electricity, and there might be some form of data. So I'm not sure, once again, in South Africa, we have got what they call ripple controllers. So you can sort of put a controller up, and then with a specific signal sent down over the power line, it'll do something like switch off the geyser or switch on the geyser or something similar just to try and save electricity. But the thing is, when we start looking at the new proposed grid, you talk about two-way communication between the customer and the utility provider. So all of a sudden, you've got every consumer actually has got some sort of endpoint with access to the utility grid. And this changes the threat profile to some extent. It extends it quite significantly and makes it very interesting. And then you've got the privacy concerns. And I believe from what I've read, I believe this is one of the major things here in the UK in terms of people who are worried about stuff. But because this stuff is being broadcast all the time, and when I start talking about the actual media, this might make more sense. But because we're permanently broadcasting usage information and similar, it basically becomes possible, and this is called non-intrusive appliance monitoring. It was published by Elias Quinn back in 2008. But basically, because of the usage, you'd actually be able to profile a specific, you'd be able to see what devices were running at any specific time. You'd be able, so for example, we'd see on the bottom left, that's the peaks when the refrigerator kicks in to keep food cold and similar. And then Tony Flick and Morehouse also pointed out you've got the whole what they termed smart stalking and smart thieves. Basically, where you'd be able to, if someone was going along and driving an electric car, apart from the fact that you'd be able to determine when they're home and what appliances they were using and similar, if they went to work in an electric car and arrived back home and plugged it in and let it charge, you'd theoretically actually even be able to determine how far they'd driven for that specific day. So it actually starts becoming quite creepy. And then obviously you've got the whole thing about smart appliances, where an appliance might register itself with the smart meter and sort of say, hi there, I'm a refrigerator. And all of this starts becoming fairly concerning. And then back in 2009, Mike Davis from IOActive published some awesome research. And the sad part is I was actually at Black Hat in 2009, but this stuff hadn't really grabbed my attention yet, so I actually didn't go and see his talk, and I'm very sorry about that. But they literally actually built a smart worm which propagated over the thing. And they simulated it in terms of the red obviously being infections, and they simulated it sort of moving across the smart meter network. And it's quite frightening that can actually happen. So there are definitely issues. And then you've got program errors, things like string copy and similar. And so this is an example from Echelon, the development kit. And STRCP appears all over the Neuron C device actually has got a STRNCPY, but I haven't seen an example of that. Not that it really matters. I'd be able to figure it out. But I mean, it's sort of almost reminiscent of back many years ago with MSDN documentation being wrong and vulnerable to SQL injection, basically teaching people how to implement things incorrectly right from the start. The interesting thing about this is also that, and it was as pointed out by Mike Davis, also goes about the fact that these devices are very limited in terms of resources. There's not that much storage, there's not that much processing capacity. So a large chunk of times what will happen is that actual error handling is not implemented to the full extent and similar. And then we all know what happened when Skynet went self-aware. We're giving these machines power to do things, and it's actually relatively frightening. Right, so I thought about this, and I got a bunch of meters. I'll explain them in a minute. And I thought, well, actually what would be nice, it'll actually be nice to interface with the thing correctly, because we can actually start looking at attacks against other devices, sort of sniffing the bus, seeing what's there, and actually ultimately even looking at attacks against infrastructure, because I'm pretty sure there's going to be a lot that is actually going to fail out of there. So I went and dug around and I uncovered the Echelon stuff. Now, Echelon's a company developed the LonWorks and LonMark, and all of this is controlled by the Neurochip, which they developed smart meters themselves, but also often found in third-party solutions. And they sold the smart meter business back in last year because they now want to focus on the industrial Internet of Things, because we need some new cliches. And they developed and standardized the LonMark protocol, which is basically called LonWorks protocol these days, or even ANSI CA 709.1. Right. There are approximately 90 million devices deployed in 2010, and you find them all over the place. You'll find them in train control systems, electro-pneumatic braking systems, fuel control, building automation, appliance control, monitoring, et cetera, and you'll shortly find them in garden irrigation, because when I'm done, that's what's going to happen. And then also because of this, I'm from South Africa. I decided I had to get this stuff to play around with. We're super cheap. I drew 100 pounds yesterday at the current exchange rate. I sort of feel fairly violated about that. But in terms of that, you actually get this thing called the mini evaluation kit, which is basically a device, comes with as a set of two, looks like that, runs on TP-FT10. I'll explain that in a minute. It's got a couple of sensors, and you can basically write applications which run on these devices using their proprietary development language called Neuron C. It's got a couple of buttons, a couple of sensors, and a joystick and a nice LCD display, and they're actually fairly nice. I rather like this stuff. So basically, they run what was termed the LonWorks protocol. Now, LonWorks, when you look at it, because there are a couple of things, LonWorks protocol actually implements sort of 6 layers of the OC stack, basically. And this is all defined in IEC 14908-1. Now, the actual physical layer is provided by the communication medium. In this case, it's TP-FT10. It's basically a twisted pair. I'll go into that in a little bit later. Now, TP-FT10 is defined in standard IEC 14908-2. It could also be rolled out with communication over power lines, which is defined in standard 14908-3, and so on and so forth. Ultimately, you can probably even run this stuff using datagrams via avian carriers or whatever. I mean, it's media agnostic. But in terms of this stuff, the actual devices I have, they run on twisted pair. Which is basically a twisted pair medium. It can run in linear bus, free topology, and it supports actually fairly large lengths. They sort of say the maximum length is 2.7 kilometers, can be extended another 500 meters. And ultimately, you're talking about 64 devices per bus. They run at 78 kilobits per second. Sort of the sort of baud rate. It's not quite serial, but that's basically how the stuff works. And what's fantastic about twisted pair is it's shared medium, which means that every device on that bus sees communication from everything else. If you plug in a probe on the thing, okay, the device will ignore information that's not destined for it. But if you plug in onto the bus, you'll see everything that's happening, and that's pretty cool. Now, according to the specs, the twisted pair actually has to be terminated. And the thing is, my tests, that hasn't necessarily been necessary. But granted, I'm only running over a piece of twisted pair about that long. I think if I ran it for 2.7 kilometers, it would probably have to be terminated because it's not going to work that well. Now, why I also focused on TP-FT10 is because I'm not an electrician. I'm not qualified to work on signaling over high power, and I rather like my house, and I don't quite want to burn it down. So in terms of this low voltage, it's easy to use, and it makes things a little easier. Now, in terms of communications, I've been living on bad coffee and cigarettes pretty much permanently for the last week because some of the stuff I implemented on a Bus Pirate, and during texting on Wednesday night, I sort of blew it up. And I've made a couple of creative hacks to actually demonstrate some of the issues. But where I stay also, we get nothing there. If I order overseas, we've got the South African Post Office. It means I pretty much may or never get whatever I ordered. If I do get it, I'm going to be waiting for 2 weeks, and I've literally just had to make a plan. So the show must go on, so all I've done is actually kept calm and carried on hackering. So what I'm going to be doing is I'm going to be demonstrate a partially working bus sniffing attack, which is, one of them is via a very creative approach. I'm actually rather chuffed with that because it's really, the purists among us will probably be very disappointed in me, but it actually does work. And I'm going to demonstrate a partially working bus injection, which is going to result in lots of bad packets. But this resulted in me finding a couple of bugs which I hadn't been aware of before of. And for example, it's possible I keep on crashing the USB driver. The USB driver, obviously, to allow me to interface a PC to the Lonwork, and it basically looks like that. But basically, when plugged in, if I'm generating tons of bad packets, it falls over all the time. And once again, I get smart meter crashes. I'll show you screenshots of that a little later. The device will keep on rebooting. And it seems to be an integer overrun, but I haven't dug into that too far yet because it's fairly difficult debugging the stuff. And then obviously I'm going to demonstrate the tool sets I'll be releasing by intercepting other digital comms. One of the things is I thought, okay, great, I'm sort of focusing on Lonmark, but I mean, it's sort of pointless writing something specifically for that. So basically you'll be able to intercept a bunch of any arbitrary two-wire traffic. Obviously, bearing in mind that you don't want to let the magic smoke escape out of your devices, so you've got to be very careful of the input voltages and so on and so forth. Right. As I mentioned, it runs over 78 kilobits per second, but the actual link is actually Manchester encoded. It's not serial. It's basically a bit stream. It uses differential Manchester encoding. I'll explain that in a bit. It's not serial, but the nice part about it is you can actually DOS the bus if you just sort of set up 58 kilobits per second and just sort of flood it. No devices are able to transmit, and obviously that's potentially got potential issues as well. As I sort of mentioned, it's also media agnostic. You don't have to run it over twisted pair. You can run it over power lines, avian transfer protocol, whatever. It doesn't really matter. And because it uses Manchester encoding, it automatically determines reverse polarity. So it makes it very easy just to plug anything onto the bus and see what actually happens, because it will automatically detect the polarity. So differential Manchester encoding, it allows you to retrieve the clock cell. It encodes the bits alongside this clock. I'm going to give you an example now. But a full clock cycle, either low or high, is going to illustrate that the sort of binary 1. And then a half clock cycle, low or high, with a bump, obviously will indicate a 0. And that's what it looks like. So I mean, you'll have a full clock. These are the sort of basic ticks. Full clock, those are both 1s. That's a 0, that's a 0. That's basically how the encoding actually works. When there's no communication happening, I mean, the little lights on the board aren't flickering, it's basically the line is undriven. And when data starts traversing the network, the first thing that happens is there is actually a byte sync, which is a series of Manchester 1s. Obviously, it'll be in the reverse state of what the line actually was. And there'll be a series of them. This is before the actual datagram starts being sent. But anyway, a series of them will indicate the byte sync. This is where we must start looking and getting ready to intercept and analyze the stuff. And then following that, there's a bit sync, which is basically a single binary 0. And after that, there will be the data. So if we imagine there might be a whole series of byte syncs, it'll suddenly be a full clock high, full clock low. Then there will be a half clock high, low, and then the data follows on from there. So it makes it quite easy to actually intercept the stuff. So after the bit sync, so both of these are called the preamble by Echelon, and I'll explain that when I show a screenshot a little later. The byte and the bit sync is called the preamble, and then you actually get the packet data. And then finally, after that, you've got the 16-bit CRC check. Anything which has got an invalid CRC will get discarded by the transceiver. Addressing, so smart nets get sort of addressed in terms of domains. The domain can be up to 48 bits long. If it's all 0, it'll send it to all domains. LikeNet with subnets, and then every node is 48 bits. So you can address things to a full domain. You can address things to specific groups of nodes, and then finally you can address things to individual devices. Lonworks also caters for authentication. Now, it's key-based, but what they say is that the keys will normally actually be allocated to devices upon commission, but LonWorks actually provides a mechanism for changing the key on the fly. And it's a 48-bit key, which is distributed via the actual protocol. And the thing here is the media is shared, so it's potentially possible to retrieve the key. Obviously, the actual algorithmic function they use in order to generate the challenge response is a very closely guarded secret. So in this case, it's not going to help too much, but still, it's basically possible. If you've got the key, we at least reach a point where we can start actually looking at how that is implemented from a black box perspective. And then following that, you've got the application level messages, which are basically just a type of struct, which will consist of a specific type and followed by data. And the actual type is defined once again in the standard. Application messages start with 00. You've got incoming network variables. So these devices communicate via network variables. If an event occurs, depending on the application, it will sort of transmit a network variable if that specific thing is bound. So you basically got two. You've got the incoming network variable, the outgoing network variable, and those are their two corresponding types. You've obviously got a bunch of network management things like changing the actual key, and then final diagnostics, which start with 0101. Okay, so that's it. Now, we've got a sort of fair understanding in terms of how the stuff works. And now we want to look at actually how do we go along and read data from the specific stuff and potentially inject data into the stream. Basically, I opted for two Arduinos, computer, obviously, because it's very difficult to type on Arduinos, and I mangle the stuff using Java. And basically, the implementation looks like that. We sort of wire up our Arduino for sniffing on the one side, the input one, that sort of goes through via COM to the PC, gets incepted by the toolset, and obviously the toolset caters for a whole bunch of stuff, and it gets forwarded back. And that basically looks like this. I don't have any Arduinos connected over here, but it'll normally give a list. I select how I want to connect to it. I sort of say, okay, well, great. What type of communication type are we dealing with? I've currently got 1, 2, 3, 4, I think, serial, digital stream, analog stream, and raw analog. Obviously, I can specify my transmit and receive pins, and if it's serial, I can specify the actual baud rate I want to intercept. Once I've connected, I can sniff just using the left-hand side. That's the receiver. The right-hand side is the transmitter, so any data coming through on the left, I'll be able to analyze in the pane in the middle, and any data I receive, I can then just go along and shunt, just push it out to the right-hand side, and that will push it back to the bus. Obviously, it's not an incredibly robust mechanism because of the fact that, apart from Lonmark is not going to be that timing-driven, but it's going to be rather difficult to intercept digital comms, which are very, very specific in terms of timing, because you're not going to have a very good chance to do that. Right. Okay. And that's going to bring me to a couple of demos. Now, as I sort of said, I've run into a couple of issues with this stuff, so I'm going to be presenting from. So in this case, what I'm going to do here, now my video quality is not particularly good, but basically this is the device. I'm just wiring up a bus pirate, and I've got a screenshot of that in a minute. But basically, we wired up the bus pirate, and now we're generating traffic by actually pressing the service pin on the actual thing. And as we press that, we'll actually see, it's very, very bad video. You'll see the actual stuff speeds up quite significantly. And that is basically what it looks like, is we reading bytes, and as we generate traffic, we actually getting this stuff back, which is pretty cool, but isn't fantastic. And that leads me to this specific one. As I said, I came up with a horrible hack to actually get the stuff working. In this case, just for demonstration purposes, in this case, I've actually wired the 2 wires up to analog, ground and analog, or AREF and analog. And I speeded up the stuff quite significantly. And basically, we'll actually see the encoded, Manchester-encoded signals as traffic is generated. But unfortunately, because it is analog, it's not specifically, it's not accurate enough in terms of to actually properly decode it. We can sort of see the stuff starting, but it's all over the place. And I actually spent a large portion of last night actually hacking the software serial interface, because I'm actually pretty close. Now, it's horrible because you've got this the software serial interface, which will actually allow me to implement this stuff natively as a library on Arduino. But the problem is it's incredibly timing specific, because obviously we're looking at 78,000 baud or bits per second. And the software serial interface, the actual timing is actually worked out in terms of the number of instructions in specific loops. So basically, you've got to develop the thing, you've got to go fire it up in a debugger, see how many instructions are in that loop, and go along and modify the code as well. So I've had good results with it, but it wasn't ready for today. Right. And then this one is basically, if we go along and we start pushing stuff onto the bus, we go along, and in this case, what you'll see is, let's actually skip back over here. You'll see I've got it, and that transmit light is burning permanently, and that's because I'm using the onboard serial port at 57K baud. That's the packet log, which I've got an image of now. I'll show you now. But if we watch over here, what we're going to see is the service light's going to come on, and the device is going to keep on rebooting. And what this means is we're actually injecting traffic, which is actually legitimate. It can be decoded. As we see, service light comes on and the device reboots. Now, if we look at the actual packet sniffer, this is Lonmark's packet sniffer, the preamble is too long. So we're getting a CRC error because obviously it's not proper LON traffic. But obviously the preamble has come through. There are too many byte sinks and bit sinks. And it's probably, as I said, it's difficult to debug on those things. It's probably actually causing an integer overrun. And that is resulting in the device crashing and literally rebooting. Okay, finally, in terms of the actual working with the actual application, we basically got what I've implemented here is basically just two Arduinos. This one, they're implementing a serial bus between the two. TTY, ACM2, and 3 are the devices I basically want to attack. And all it's doing is it's writing information between device to device. And I'm debugging this. I've got a thing sitting, reading the information out. Now, in the first case, when I want to start sniffing this stuff, I literally take my one digital proxy Arduino. I hook it up to the outputs of that, obviously observing voltage stuff, or it could crash quite easily. And basically, I connect to this using my application. And basically, I can immediately start seeing what's actually happening on that specific bus. So it makes it a lot easier. I can actually start going along and reviewing that and seeing that in terms of what is the physical information being transmitted at any specific point in time. And we can take this further. As I sort of said, we can intercept and move this on. So basically what I've done now is, obviously this is one of the devices which is communicating with this device. I've got this device hooked up to my laptop, and I have the device on the right hooked up to my laptop. And basically all I'm doing is I'm putting myself in between these two devices. Obviously, as I said, it's not going to work with a bunch of binary protocols, but I've had fairly good results in a bunch of stuff. And this basically allows me to intercept the stuff, modify it, and forward it on. So that's basically pretty much like Web Scarab for binary protocols. So in terms of the tool set, I'm going to be releasing them shortly. I've got to build a couple more JNI components for for Windows and OS X and stuff like that, but they'll be published on Git by next week probably. And you can just watch our blogs, our blog site for the actual post. And yeah, so the big thing over here is there's really a lot to shoot at in this field, and stuff is going to break, both on the actual device side and on the backbone. And also in terms of that, never release the magic smoke, because it means your demos don't work quite as planned. But anyway, that's it. Questions?